Put that thing back where it came from, or so help me do. Let's do a full hypothesis test. This one we're going to test our oven. You see, my wife says that if you set the oven to 350, the actual average is less than 350. I mean, you've got opening the oven door and all sorts of crazy things that go on, which means it's okay to leave the cookies in there for a little extra. Well, let's find out. So I test it. I randomly select 20 times. Now that part should jump out at you. We only tested the oven 20 times. What that means is we might not be able to do this unless we have normality somewhere. And it says assuming normality right there. So yes, we're good. But do keep an eye for that. If you waste your time on a problem that can't be done, you're going to be frustrated. We had an average of 350.65, so close to 350. But is it close enough? Well, we know our sigma. How do we magically know this sigma? It's magic. I just told you it was magic. How did you not pay attention to that? We are not ready to kill sigma yet, but at some point we're going to talk about the idea of what would we do if we didn't know sigma. And we want to do the test. So let me start with my null and my alternative. It's actually a good idea to start with a picture, but I'm skipping that on purpose. Our null and alternative are going to be about mu. The average is what we're testing. But here is the question that we're trying to do. Is it actually less than 350? Those words are less than 350. Notice I'm not using the 350.65 in my hypothesis. That came from my data. This is a random value that would change every time we did this experiment. And so this is a statistic. We want to put parameters here. Now that I know my alternative is less than, I can fill in the null, which is the opposite. It's a greater than or equal to, and 350. These numbers always match. If they don't match, you've messed up. Now, let's try to decide what alpha we should use. And remember, this is the happiness of my wife at stake here. So my alpha is going to matter to me in this case. Let's draw the picture of what's going on. That'll help us see what a type 1, type 2 error would be. 350 is my hypothesized parameter. That's the real average. And I landed close to that, but I know this guy right here, which is 1.2 over the square root of 20. Now, where is my alpha region? This alpha region is the less than region. So I have a left-tailed test right here. So somewhere I'm going to draw my line. What happens if it lands close to 350? What am I going to tell my wife? Well, she said it was going to be less than 350. If it lands right on 350, I'm going to say, I don't think so. But if it lands way beyond 350, this is where I say, you're right. And after 14, 15 years of marriage, a long time of being married, I can tell you I want this area to be as big as possible so that these are the words coming out of my mouth. So what am I going to do? I'm going to increase this alpha. This large alpha is going to help make my marriage happier. So I think I'm going to go with something like 0.15, which really is about as large as your alpha should really get. I have seen bigger, but that's pretty extreme. So this area right here is 15%. Next, I'm going to do a z-score. Here's my x bar minus mu. There's my standard error. I get a z-score of 2.422, which gives me a p-value of 0.99. That can't be right. That's way too big. It must be that I want this side. Don't fall for this trap. If you're not relying on the picture, which I've slightly been ignoring a little bit for this very reason, it's easy to get the p-value mixed up. Look at what our pick for the area. We are doing a left-tailed test, and we got a positive z-score. So we are 2.42. We are clear up here at 350.65, and it's a left-tailed test. So the p-value here is actually all that area. It should be huge. Why is the p-value so huge? Because we were hypothesizing on the complete wrong side of the distribution. And you might feel this instinct to say, oh, let's change the question. Let's make it a right-tailed test instead of a left-tailed test. Well, you can't. The question was decided before you gathered data. And so these kind of p-values can happen. our actual p-value here is 0.99228, which is a big p-value. Definitely failed to reject. You can see that in the picture. We're nowhere near the rejection region. We're clear on the other side. So this is very important, guys. Listen to me. It's important that you do not say you're wrong. That would be like saying accept the null. No. What you say is, well, this data isn't the data that can show that you're right.